Okay, so I want to tell you, so why is L a number like 0, 1, 2, on up to, I'll have to tell you the bound, but, and why is M sub L bounded by L? So that's the end, right? It doesn't continue, and this also has an end. Why these quantum numbers? The reason is because Schrodinger's equation, when you solve it, you end up getting, when you solve it for the wave functions psi, you're going to end up solving for wave functions in spherical polar coordinates. So r, theta, phi. Let me remind you of r, theta, and phi. So in a right-handed coordinate system, here is an example of a right-handed xyz coordinate system. So I'm going to draw a vector in it. Let me just draw it stuck out here. So here is some vector, and I'll call it r. If I drop an altitude, I drop that altitude parallel to the z-axis, right? That's how you drop altitudes. So when I drop the altitude, I can look at the projection of the r vector, the shadow of the r vector, on the xy plane. So the xy plane, or actually the angle phi, it's called the azimuth, azimuthal angle, describes how to go towards the y-axis from the x-axis. So phi is that, you read phi this way, and phi takes values in between 0 and 2 pi. The other angle, the polar angle, is called theta. You read it by starting at the positive z-axis and going down to your vector r. With the smallest angle or the shortest path or whatever. So this is the angle theta. It's called the polar angle. And you can see, because our coordinate system matches z with the polar angle, z is special. So also the polar angle theta has a boundedness as well. It's bigger than or equal to 0, less than or equal to pi, So anyhow, we don't need theta to be described outside of 0 to pi, and we do not need phi to be described outside of 0 to 2 pi. So these are bounded intervals on the angle. And when you have bounded intervals, it's really similar to a bounded interval in confinement. And this is a subject described in Chapter 5. Bounded intervals in confinement, you get a quantum number n and an energy level spectrum, a discrete spectrum. In this case, these bounded intervals in the angles give rise to a discrete spectrum in the associated angular momentum. And then this is related to the z component of angular momentum. And the z component is chosen out to be special because of our relationship of, or our pick of the z-axis to be the polar axis that the polar angle is read from. So it's an accident of choosing our spherical polar coordinates to pay attention to z in a special way compared to x and y. You can see that the angle phi explores the xy plane sort of symmetrically. Yeah, so x and y are very similar. And so even though we may say what the z component of angular momentum is, we are not able to describe the Lx and Ly separately. Yeah. So you're going to keep reading in this book, and you're going to see the separation of variables happen. So this right here is the Cartesian coordinate x, y, z. This is not separable. But if you rewrite this second derivative operator in 3D, you rewrite it in terms of r, theta, and phi. It's crazier looking. It's way bigger and more complicated seeming. But it turns out that when you write it this way, it is separable. And this is extraordinary. This is real cool. So this differential, the wave function can be written separably. And if you feel like it, go and try to take this crazy differential equation and show that you can reduce it to 3 separate differential equation problems. Essentially what you're doing is you're showing that you can have a separable solution written as a function called r times a function called theta times a function called phi, where they each depend independently on their own variable. Then you go and you solve 3 different differential equations. And here are some answers for the differential equation that's strictly in R. You can see that they showed you the separable. This is the separable differential. This is the differential equation strictly for the R part of psi. And it shows you a bunch of answers for R. But what's really interesting about R, let me show you this, is earlier in for example chapter 5, when you were first exploring Schrodinger's equation, you saw that we had to, for example, describe a wave function by the quantum number. So this was the wave function, say, for the ground state or the first excited state, etc. When we went into the two-dimensional, for example, infinite well, the two-dimensional infinite well, we actually had to describe, two different quantum numbers. So we had wave functions that were labeled by 2 different quantum numbers. In this case, we're going to have a piece of the wave function, capital R, that actually needs to be described by 3 different quantum numbers. So we have to go in for R. You can see them doing it here. R for 1, 0, 0 is this crazy function with this exponential. R for n equals to 2, L equals to 0, m sub L equals to 0 is this function instead. If you bump L up to 1, you get this function instead. If you bump L up to 1 and also change m sub L up to plus or minus 1, you get this business that doesn't seem to be dependent on the plus or the minus 1. But you can see actually that they also include the theta. So, yes, yeah, so that this is the way this goes. So, let's see, you know what, I kind of, I said something wrong. So instructively, actually this R function is only dependent on 2 of the quantum numbers. This capital theta function, so the theta factor of the separable solution, you can see it here actually in equation 7.14. It's only dependent on L and m sub L. So this is L and m sub L. And then there is the phi factor of the function, and it's only dependent on m sub L. Yeah, so I misspoke earlier. So if you product these things together, you get the full wave function, which is specified by 3 quantum numbers, and it's the full dependence. So what happens for the rest of the chapter is you study degeneracy. You think about how many different sets of quantum numbers have the same energy. Then you go, and this is pretty cool. It's an exploration of the shapes of the wave functions. You can see that this is somewhat similar to the one-dimensional Coulomb potential that the chapter starts off with. So these pictures here are real similar to these pictures here. I don't know if you can see that in the camera. So these pictures are in the one-dimensional atom. These pictures are the capital R function or factor in the full wave function. So you go on, and there's probability. So here's a probability, and then, and also probability and angle. But the world gets super interesting when we start talking about the intrinsic spin of the electron. So I'll leave you to go read. In particular, this right here is a huge deal, this Stern-Gerlach experiment. I wonder if they got Nobel Prize for this. Let's see. Oh, I don't see. But anyways, the Stern-Gerlach experiment is a description of an experiment where you can learn about the quantization of electron spin. Yeah, nothing about Schrödinger's equation and the classical atom gives rise to spin. Spin is a purely quantum mechanical thing. It's fundamental to the electron. It's as fundamental to the electron as the mass of the electron or the charge of the electron. It shows there's a space quantization of the spin of an electron. And then it goes on to study spectroscopic notation, where the SPDF, GHI, you tend to see the periodic table of elements. You describe electron orbitals with these spectroscopic notations, SPD and Fs. And it describes some energy level labeling. It describes this thing called a selection rule, which is pretty amazing. And its association with the probability to see an atom transition. And then it goes into a couple of ideas. One is called the Zeeman effect, and the other is called the fine structure. So I invite you to go read about those things. And yeah.